Myself, Dr. K. Viswanath Allamraju, Professor at Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. So far we covered introduction of shear force and bending moment diagrams, types of supports, types of beams, types of loads, and some of the problems we solved on cantilever beam with point load, cantilever beam subjected to UDL, and cantilever beam subjected to combination of both UDL and point load or concentrated load. And today we are going to study few more problems on the case of simply supported beam. Suppose the simply supported beam is subjected to complete uniformly distribution load. So here the uniform distribution load, this is the simply supported beam, consists of UDL throughout the span. The span of the beam is L. L is the span of the beam. And what is the UDL? The UDL is W per unit length. That is small w, small letter W per unit length. And how the shear force and bending moment varies when simply supported beam is subjected to UDL. Let us see. Here it is. The simply supported beam. Whenever simply supported beam comes, we have to find out the reactions at the support. Here there are two reactions are there. Number one, that is reaction at A and reaction at B. Both are vertically upwards. How can we know whether it is acting vertically upwards or downwards? It doesn't matter. But let us assume it is both are acting vertically upwards. The way we assumed it is vertical upwards, the results are coming positive, then our assumption is correct. If the results comes negative, then that means our assumptions are wrong. But the values only direction will be changed, but values remains same. Now, by using two equilibrium equations, sigma FV, algebraic sum of all vertical forces equal to 0, and sigma M, that is moment equilibrium, that is algebraic sum of moment equilibrium about any arbitrary point equal to 0. By using these two equations, equilibrium equations, we are going to find out two unknowns. Here, what are they? The unknowns are reactions at A and reactions at B, point B. Let us find out. Let us equate. Now, let us go for calculating this reaction at A and reaction at B. That is RA plus RB equal to what is the total load? That is W into L. So here the both are acting at the same equal points. RA and RB both are acting at equal. So here now RA equal to RB equal to same equal lengths, that W L by 2. Now we have to find out the shear force at a distance x we are going to calculate. Because why we are going to calculate at a distance x? Because there is no loads are acting in between concentrated loads, but UDL is acting. So we are considering how the UDL is varying at a distance x. So by considering that at a distance x, now Fx equal to this reaction at point A, you can consider the shear force lines. This is a positive shear force sign convention, and it is negative shear force sign conventions. So, as we are taking from left direction to right side, we are moving here, calculating. Now at RA is upward direction, so positive, that is plus RA minus, what is the UDL here, reacting W per unit length, and at the distance W per unit length into X, that is WX, or the RA minus WX. What is the reaction at A? We already calculated. Substitute over here, that is WL by 2 minus WX. This is the value at a distance X. Now we understood at a distance X variation. Now if X equal to some 0.5 meters or X equal to L by 2, then what is at Fx equal to L by 2, that is middle of the beam. So at x equal to 0 and x equal to L by 2 and x equal to L, substitute over here, then we'll directly get it, the shear force value. Now at x equal to 0, what is x equal to 0? That is x equal to 0, that is at A, that is point A. X equal to L by 2 at point C, and x equal to L, that means that is the point at point B. So x equal to 0, if you substitute over here, that is WL by 2 minus W into 0. That is what happens, WL by 2. Reaction at A is shear force, at point A is WL by 2. Reaction at L by 2, that is at half of the distance of the beam, that is WL by 2 minus WL by 2. Then what happens here? In the middle, shear force is 0. And x equal to L, WL by 2 minus WL by 2, WL, that is minus of WL by 2. It is negative value at at point B. At point C, it is 0. At point A, it is a positive value. We can understand, we can observe the shear force values at different distances. At x equal to 0, that is a point A. Shear force at point A is 0. Shear force at point A, that is W plus positive value WL by 2. At x equal to L by 2, half of the distance point C, that is 0. At x equal to L, that is negative WL by 2. Let us draw the shear force diagram by using those values. So here you can see in this figure, this is the baseline we have to draw initially. This is the baseline. After the baseline, at x equal to 0, there is a point A, that is WL by 2. At point C, mark it as a 0. And at point B, that is negative WL by 2. It is going downwards. Now, what type of load it is acting here? That is UDL is acting. UDL is acting means it is dependent on length here. So that's why you have to join these two points passing through the point C. Then what happens? This is the way shear force diagram can be drawn. So here positive. So this positive is coming from, it is maximum at reaction at A and coming 0. There is no effect of this reaction. So this is the point C where there is no effect of shear force on this beam, on this structure, on this simply supported beam. So shear force is completely 0 here, and it is negative at point B, and it is positive at point A. So there is no effect of this load. This UDL effect is 0 over the midpoint of the beam, simply supported beam. Now, how to draw the bending moment diagram? By using sign conventions of bending moment. Let us see bending moment diagram. Again here there is no values mentioned, quantity values, but we are taking in terms of x value, how it is bending moment is being varied in proportional to the x. Let us assume it is a section x, how the bending moment is varying. Here RA, what is the reaction? WL by 2, and it is WL by 2. So reaction, what is the bending moment at point at section x, at point x, that is mx. That means RA into reaction at A into x distance minus, why it is become minus, this load is acting downwards. This is moment is upward direction, upward is positive RA into x minus, what is that UDL? We have to know it. That is W into small x into x by 2. That is RA into x minus WX square by 2. This is the variation of movement of the simply supported beam when it is subjected to UDL at a distance x. This is the equation of bending moment variation. Now, if you substitute x equal to 0 over here, that is at point A, that is bending moment at point A, that is x equal to bending moment at point A, it is 0. bending moment at L by 2, what is MC? That is RA, that is W L by 2 into L by 2 minus W by 2 into L by 2, that is L square by 4. That is W L square by 4 minus W L square by 8. That is nothing but W L square by 4. So we can understand here the bending moment here W L square by 4 at midpoint. And what about at B, at x equal to L? Substitute over here x equal to L in this equation, x equal to L. Then what happens? WL square by 2 minus WL square by 2, that is equal to 0 at B. At point B, bending moment is 0. So, in the case of simply supported beam, from these, by observing these values, at point A, it is 0. At point B, moment value is 0. But it is maximum where? At point C. Point C is the midpoint of simply supported beam here. Midpoint of middle. So at the middle, the maximum value is observed. So let us draw the diagram. From this equation, it is varying according to parabolic law. This bending moment is varying according to parabolic law. That's why we have to draw here the parabolic curves. Yeah, we can see at A and B 0, and it is WL square by 4, WL square by 8 minus, that is WL square by 8. It is positive value, WL square by 8. Now, let us see here how this is varying in this diagram. If we keep it over here, this is the diagram. We can see how it is being varied. The maximum 0 at point A and at point B, but it is a maximum at where? In the midpoint. Now, if we compare both shear force and bending moment diagrams over here, you understand there are very important points we can interpret here. What is the interpretation? At point C, shear force is 0. But at point C, what is the bending moment position? The position of bending moment is maximum. At point A, shear force is maximum value. But whereas at point A, what is the bending moment? 0. At point B, shear force's value is there. At point B, bending moment is 0. So, here bending moment is acting at this point. But shear force is not acting. In this case of simply supported beam, when it is subjected to UDL, uniformly distribution load. So, whenever UDL, uniformly distributed loads, are acting throughout the span of the beam, at the midpoint, the shear force becomes 0 and bending moment acts maximum. So at the endpoints of this simply supported beam, endpoints bending moments are 0, but shear force is also acting maximum values. So this is the conclusion we can understand. It is very important problem. In order to understand the variation at the effect of shear forces and bending moments when it is subjected to uniformly distributed load throughout the span of the beam. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.